and creep in structural materials. Welcome to Blueprint to Reality, where we break down complex engineering concepts into easy-to-understand lessons. In this episode, we'll dive into fatigue and creep, two crucial phenomena that affect the longevity and safety of materials used in structural engineering. What is fatigue? Fatigue is the weakening or failure of a material due to repeated loading and unloading cycles, even if the loads are below the material's yield stress. Over time, these repeated stresses can cause small cracks to form in the material. These cracks grow incrementally with each load cycle, eventually leading to catastrophic failure. For example, think of bending a paperclip back and forth. Even though the paperclip is not under extreme stress, the repeated motion causes the material to weaken and, eventually, it breaks. This is a simple example of fatigue failure. In real-world engineering, fatigue can occur in structures like bridges, airplanes, or machinery, where components experience repeated loading due to traffic, wind, or operation. Why does fatigue matter in structural engineering? Fatigue is crucial to understand because materials may appear to be in good condition based on a one-time test or inspection. However, over time, repeated loading can cause cracks to form and grow, leading to unexpected failures. Engineers must design structures to withstand these cycles of loading and unloading. This includes ensuring that materials used in key components are resistant to fatigue and that the structure as a whole can handle dynamic forces like wind, traffic, or vibrations. What is creep? Creep is the gradual, time-dependent deformation of a material under constant stress, typically at elevated temperatures. Unlike fatigue, which is related to repeated loading, creep occurs when a material is subjected to a continuous load over an extended period. For example, imagine placing a heavy weight on a rubber band and leaving it for hours. Over time, the rubber band will stretch and elongate, even though the load is constant. This is similar to how creep affects materials at high temperatures or under constant pressure. In structural engineering, creep is particularly important in materials like steel, concrete, and polymers, especially in applications where components are under continuous load, such as in high-temperature environments like power plants or in concrete structures subjected to sustained loads over years. Why does creep matter in structural engineering? Creep is important because, over time, the material will continue to deform, which can cause failure if not properly managed. Structures that experience high temperatures or long-term stresses, such as nuclear reactors, turbines, and bridges, must be designed with materials that can resist creep. If creep is not considered, it can lead to issues like 1. Distortion of structural components. Over time, components can elongate, bend, or change shape, compromising the integrity of the entire structure. 2. Loss of load-carrying capacity. As materials deform under sustained load, they lose their ability to carry loads, which can lead to structural failure. How do we measure fatigue and creep? Both fatigue and creep are typically measured using specialized tests. 1. Fatigue testing. In fatigue testing, a material is subjected to repeated loading cycles at various stress levels. Engineers track the number of cycles it takes for cracks to form or the material to fail. This is used to establish a fatigue limit for materials, which is the maximum stress level below which the material can theoretically withstand infinite cycles without failure. 2. Creep testing. In creep testing, a material is subjected to a constant stress at an elevated temperature over an extended period. Engineers measure the strain or deformation over time to determine the material's creep rate and predict how it will perform under long-term loads. Both tests help engineers determine how materials will behave under real-world conditions, ensuring the structural components will last for their intended lifespan. Fatigue versus creep. Key differences. While both fatigue and creep lead to material failure, there are key differences between the two. Loading type. Fatigue is caused by repeated loading, while creep is caused by constant loading over time. Time frame. Fatigue leads to failure after a relatively short period due to cycling stresses, while creep develops over a much longer period under continuous load. Temperature sensitivity. Creep is more significant at high temperatures, while fatigue can occur at ambient temperatures but is also influenced by vibration or dynamic forces. Real-world applications. In aerospace engineering, fatigue is a significant concern. Airplanes experience constant vibrations and pressure changes during flight, which can cause fatigue failure in critical components like wings, fuselages, or landing gear. Engineers use fatigue-resistant materials and design strategies to ensure the airplane can withstand millions of flight cycles without failure. In civil engineering, creep is a concern for long-term structures like bridges and concrete buildings. Concrete, especially when subjected to high loads over extended periods, can undergo creep, potentially causing deformation and damage to the structure. Engineers often use reinforced concrete and carefully manage the load distribution to minimize the effects of creep. Similarly, in power plants, materials like turbines and pipes are subject to high temperatures and continuous stress, making them susceptible to creep. Engineers select materials with low creep rates and carefully monitor their performance to avoid failure. Conclusion. In summary, both fatigue and creep are important factors that influence the durability and safety of materials used in structural engineering. Fatigue arises from repeated loads and can lead to cracks and failure over time, while creep is a gradual deformation caused by sustained loads at high temperatures. By understanding these phenomena and accounting for them in material selection and design, engineers can create structures that are both safe and long-lasting, ensuring their performance even under challenging conditions. Thank you for tuning in to Blueprint to Reality. If you found this explanation helpful, don't forget to like, share, and subscribe for more civil engineering insights. See you in the next episode.